Hi guys, last time we discussed geometric modeling in general. We discussed different ways how to represent shape in a computer memory and how to work with a shape. We also introduced boundary representation as a standard de facto technique for modeling, and now it's time to talk about OpenCascade. So let's start, let's see what do we have in OpenCascade, and for more reading I invite you to visit my blog, which covers different aspects of the library and different things around geometric modeling in general. Here I put a quotation which I found on the official website of OpenCascade, and it nicely explains what OpenCascade really is. So we read here that although there are many libraries for displaying graphics on the scene, OpenCascade's real function is to do the math. And I couldn't say that better, because there are many libraries which allows you to visualize 3D stuff on your scene, but there are very few libraries which allows you to design objects, especially when it comes to analytical representation of geometries. And that's a real function of OpenCascade. The real function of OpenCascade is to serve as a solid, and not only solid actually, also surface modeling library. And now we are going to talk about the modules, which is a higher level look at the architecture of the library. Actually, understanding of modules is pretty important, because when you know how library is composed, it's easier for you to find out the functionality which you are looking for. You could easily navigate over the modules of OpenCascade and quickly find the function you are looking for. Here on this picture we have the main modules illustrated. So the fundamental module is foundation classes. Let's see what foundation classes module contains. First of all, it comes up with smart pointers. Back in the day, smart pointers were not available as a part of C++ standard library, and that's why OpenCascade came with its own implementation of a smart pointer mechanism. The idea of a smart pointer is to behave like just a raw pointer, but you do not care about releasing your dynamic memory. Like whenever you allocate something which inherits from standard transient base class of OpenCascade, if you wrap it with a handle, if you wrap it with a smart pointer, which is called a handle in OpenCascade, you do not care about memory, you do not care about, things like deallocations and garbage collection, everything. So that's pretty handy thing. And this smart pointer mechanism is not restricted within the boundaries of the library itself. You can inherit your own classes, subclass and the standard transient base class, and you can benefit from this mechanism. Then in foundation classes we have memory management, we have operating system dependent stuff like things related to file system, to iterating files on file system, to working with threads and processes, all those things which are operating system dependent. And to remind you, OpenCascade is a cross-platform library, so you can use this layer of abstraction on whatever operating system among the popular ones. Then the fundamental piece of foundation classes is math kernel. Here in math kernel we have different functionality to work with bounding boxes of our objects, to evaluate elementary curves and surfaces. Also we have this bounding volume hierarchy thingy, which is a very amazing accelerating data structure which allows you to speed up your computation tremendously. This is especially useful for applications like ray tracing, or even in some traditional computations, like whenever you want to project a point on a mesh, for example, or whenever you want to intersect the meshes, like you can build up your fast collision detection system using this BVH approach with BVH data structures. And in math kernel we have a bunch of numerical methods, which we are going to uncover a bit later. Also, as a part of foundation classes, we have some fundamental services. Actually, in foundation classes, we have declaration of all the basic types of the library. Then we have progress indication mechanism. We have like a plugin loading services. We have different types of collections, including vectors, lists, data maps, and all those things. And also there is units API, which allows you to work with measurement units with different physical entities and to convert from SI to, imperial system. Speaking about modeling, we have solid modeling functionality and surface modeling functionality. These functionalities and these tiers are not that explicitly divided in the library, but I wanted to put it in that perspective because it's pretty important to understand whenever we speak about solid modeling or surface modeling. And both approaches, both sets of functions work with boundary representation, which is a primary representation scheme in OpenCascade and actually in any other 3D CAD engine. For data exchange, we have two principal translators. One of them is step translator, which is the most valuable one, and then we also have IGES translator. Both these translators are available as readers and writers. They can read not only geometry but also some metadata, and all of them work with boundary representation. So you would expect to read and write exact geometries of your product, exact geometries of your CAD part. And there is a bunch of mesh-based format, but we're not going to speak about this a lot because OpenCascade is not unique in this regard, and there are many implementations, including, open source implementation for those mesh formats like OBJ, GLTF, and all those, STL and VRML and all those formats. Then there is Mesher. Mesher is pretty important part of the library, and it can also be attributed as a part of modeling actually because of the key role it plays in the entire modeling workflow. Like whenever you want to visualize something on a scene, whenever you want to render your 3D object, you're not going to render boundary representation directly. You rather switch from boundary representation from your analytical shapes to facets. Like you build up a triangulation and then you visualize those polygonal data set instead of analytical cylinders, planes, all those splines and everything. OCAF is probably the most underrated functionality of OpenCascade, but it's pretty handy actually, and I use it a lot personally. OCAF stands for OpenCascade Application Framework. You can take it as Rapid Application Development Framework, and it allows you to organize your engineering data in a hierarchical fashion. You can build up a hierarchy of your domain data, and if you are using OCAF, then you get a bunch of functionality right out of the box. Like you can have open and save services, you can read your engineering data from file system, you can serialize it back to the file system. Then there is a pretty amazing transactions mechanism, which allows you to organize your algorithms in a transactional manner. Like whenever something goes wrong with your modeling API, for example, whenever your algorithm throws an exception or returns some error state, you can just roll back the corresponding transaction if you had it enabled, and this way you can get back to the previous consistent state of your session. OCAF serves as a sort of, in-memory, NoSQL database engine actually. And also it comes up with undo-redo functionality, like you have a stack of deltas, and you do not have to implement this undo-redo functionality, which is pretty classical for desktop application by yourself. Also, if you are looking for some parametric engine, if you want to build up like a dependency graph, you can also consider OCAF for that purpose. For visualization, we've been talking about visualization in one of the previous lessons. So what we have there is we have application interactive services for visualizing our shapes, and we also have a small framework which is named Mesh VS, which is Mesh Visualization Services. It allows us to visualize also surface meshes. Foundation classes. So let's speak a bit about foundation classes, and here actually we have a snippet from Visual Studio, and here we see that foundation classes is basically just a couple of libraries. One of them is tkernel and another is tkmath. Foundation classes is a real backbone of the library, and all other functionality of OpenCascade builds upon foundation classes. Like then we have modeling, data exchange, visualization, and OCAF. So in foundation classes we have a package for linear algebra. Like any geometric modeling kernel has to solve some standard computational tasks, like to solve systems of linear equations, for example, and for that OpenCascade comes up with its own implementation of linear solvers. It can also compute eigenvalues and vectors and singular value decomposition. And I think there is something else in there. Then for optimization, whenever you want to find function roots, for example, or whenever you want, for example, to project a point on a surface, you are going to optimize something. You are going to use something like Newton iterations or quasi-Newton iterations like BFGS or any other variations of local optimizers. And there is also a global optimizer, which is a particles form optimizer, and one implementation of it is available also in OpenCascade. Then we have approximation in interpolation functions in OpenCascade, which allows you to build up smooth functions out of discrete data, or you can also reapproximate like a continuous function. For example, if you have an offset surface, it doesn't have like a polynomial representation, but you can approximate it in polynomial basis. Then modeling. As I mentioned, for modeling we have two tiers of functionality. One of them is surface modeling, and in surface modeling what we can do, we can build up different types of kinematic surfaces like pipes. We can also build lofting or skinning surfaces. We can fill contours of edges or curves by surface patches like splines, and we can build offsets and something else. For solid modeling, what we can do, we can build up a prism, which is a pretty fundamental thing where you normally start from. Because whenever you do your CAD design, you basically start from a sketch, which is a planar contour, and then you extrude it to build up a prism, which would represent like basic block for all other features. Then we can also tweak faces in our prism and give it like a draft angle. We can run Boolean operations, of course, and this is a key functionality of OpenCascade, I'd say, because it allows us to perform whatever sculpting operations we want. Also, we can build fillets and like blends between neighboring faces, and we can build chamfers. As I mentioned, whenever we want to display our CAD part on a scene, we do not really represent it as it is. We do not kind of draw the boundary representation itself, but if you want to leverage our graphical processing unit, what we need to do, we need to switch from boundary representation from all those analytical shapes to faceted representation, to polygonal representation of our geometry. And that's the function of the mesher. That's what it does. So here on the right, we have a set of triangles generated by the OpenCascade mesher. So you can see here that it's a sort of sparse triangulation. We have minimal set of triangles which are sufficient to represent our geometry with a certain level of accuracy, and we can tweak it, we can make it more or less accurate because we can control the precision of the mesher. And this way we can basically generate different levels of detail. And you can see also that this meshing is kind of adaptive, because in curved areas it generates higher density mesh, and in the flat regions where we have zero curvature, the triangles are kind of coarse. For data exchange, as we already know, there is a bunch of services, and one of the most valuable functionality of OpenCascade is its ability to read and write step files, and for that OpenCascade exposes a bunch of static variables, which allows you to configure different aspects of a translator, like you can specify the units of measurement. You can also configure how would you like to process assemblies. Would you want them to be imported as a part, as a single object, or do you want to keep like a hierarchy of nested compounds? And there are many other aspects of data exchange which allows you to fine-tune what is going to happen. Like, do you want to store only 3D curves of your model, or would you also like to store parametric curves, and this way to have like a dual representation of all your edges, for example. The data exchange module of OpenCascade allows you to read and write not only shapes but also some metadata, including assembly hierarchy, colors, names and layers. And actually OpenCascade's data model, which is a boundary representation implementation of OpenCascade, it's sort of minimalistic. It doesn't allow you to store any user-defined attributes, and that's why here OCAF is employed. Here we use this OpenCascade application framework, and this way we build up a sort of hierarchy where we can store not only shapes but all the metadata coming from, you know, like a step file or IGES file, or actually whatever file, because here we have a unified data framework, we have a unified data format or storage, which allows us to treat different metadata in a sort of unified way. Like we have a hierarchy of our products, we have this assembly hierarchy in there, and we can also have different sections of metadata including colors, and also for step protocol AP242 we can store geometric dimensions and tolerances if they are defined. And actually this is an extensible thing. You can also store your own metadata, you can also store your own attributes in there. Like if you want to store some kinematics, for example, or I don't know, materials, whatever, you can put it just in the same document, in the same hierarchy. Then OCAF. OCAF is OpenCascade Application Framework, and the main entities in OCAF are application and document. So basically you can think of OCAF as of a sort of hierarchical database engine, which lives, this database lives in memory. It's not file-based, it's not giving you any query language, but it allows you to build up your engineering applications, especially if you are looking for a kickstart to develop your desktop application. OCAF is a pretty handy thing, and personally I use it a lot. So we have application entity, and the purpose of this entity is simply to manage a series of documents. What is a document? You can think of a Word document or any other document in an Office application. That's basically the same idea. Like you have a document and you put all your engineering data into that document. And the document itself is a hierarchy. And there are two main entities in this hierarchy. One of them is label, and label is something to express the hierarchy itself, because hierarchy is a hierarchy of labels. And the real data is stored in what we call attributes. So in OpenCascade there are different attributes to store your shapes, triangulations, and different primitive data types such as strings, double values, integer values, and all those things. But you're not restricted with that pre-implemented set of attributes, because you can also derive your own attribute. And still you can benefit from the services of OCAF, like undo, redo, and transactional mechanism, and all those things. In order to start using OCAF, you should think about your domain data at this elementary level. You need to decompose it, you need to define a scheme. How would you store your data in a hierarchical fashion? And then you need to decompose your data chunks as attributes. And if you want to work with your data at the very low level, you can just take advantage of the pre-implemented attributes which are available in OpenCascade. And if you want to make it more handy, for example, you can derive your own custom attributes and put them into this hierarchy of labels. Speaking about OCAF, it's necessary to understand the level of abstraction which it brings to the table, because OCAF itself is a very low-level thing. It allows us to express our domain data, our data model, as a hierarchy of data tuples. Like you have this hierarchy of labels, and you have these attributes which are associated with those labels. And then if you want to bring more object-oriented design into this whole business, you need to work with these data tuples in some more, object-oriented way. And this is where you can implement your own services to read and write data to OCAF. And here we have this data access object pattern, which should be pretty familiar. And actually this whole architecture should be pretty familiar to people who ever worked with enterprise applications. Because after all, OCAF is a sort of hierarchical database. Of course, it's tailored to OpenCascade, and it has its own, specific things to keep in mind. But the very idea of OCAF is pretty straightforward. It's just a low-level framework to organize your data. And then on top of these data access objects, you can have a layer of services which implements your business logic. So it's up to you to decide what should happen. For example, if you delete an object, should you somehow alter all other objects in your project? Should you do something else? Should you provide some specific treatment for your properties and all your objects and all those things? For visualization, we already grasped the very idea of visualization. We already practiced it in one of the previous lessons. So the very idea of visualization is that you get a lot of functionality to visualize your 3D geometries in different display mode, and you also get the selection mechanism right out of the box. And this is where OpenCascade offers a lot for you to release you from the burden to re-implement this whole thing from scratch. In the file system, if you look into the working directory of OpenCascade, you will find out that there are many folders, there are many directories in there, and these directories are named packages in OpenCascade, and each package, it's a container of classes, and all those packages are then grouped into what is called toolkit, or you can also think of a toolkit as of a dynamic library. And those libraries, in their turn, they are organized in the modules. Now, to conclude this talk, I'd like to give you some references so that you can get some more information about solid modeling in general, and you can also read about different aspects of CAD modeling systems, not only geometric kernels, but real CAD systems. If you skim through those papers, if you skim through those monographs, you will find out that all libraries and all kernels, they are kind of similar. They all expose the same sort of functionalities, and OpenCascade here is not unique. The uniqueness of OpenCascade comes from the fact that it's open source library. It's only open source library for geometric modeling and for CAD modeling. So enjoy the library, and if you have any questions, then feel free to post your comment right below this video, and next time we are going to do some more practical exercise.